Hello everyone, my name is Brian Wang. I'm from the University of Toronto. Today I'm excited to talk to you about Screen2Words, automatic mobile UI summarization with multimodal learning. This work was done during my internship at Google Research with my mentor Yang Li and colleagues Gang, Xin, Zhou, as well as my PhD supervisor Toby Grossman. In this paper, we propose a novel user interface task called screen summarization. The idea is pretty simple. Given an input mobile screen, our goal is to process the input and generate a short phrase of natural language that summarizes the UI. To achieve automatic screen summarization, we started by collecting a large-scale dataset dedicated for the task. We then trained a set of deep learning models to generate the screen summaries. So first thing first, let's talk about the dataset collection. We created a UI corpus from the RECO dataset, including Android UI screenshots and the view hierarchy that contains each element's properties. We then filtered the dataset to remove screens with inaccurate view hierarchies, which results in more than 22K screens for labeling. To annotate the summaries for each screen, we designed do's and don'ts to guide labelers write concise summaries that focus on the functionality of UIs. The guidelines were adapted from the Coco Caption dataset, a popular image captioning dataset, and we refined the guidelines through multiple rounds of pilot studies. And here's our labeling interface. It presents a mobile screen image, the labeling guidelines, and the app description to provide context of the screen for labelers to annotate data. Once the labelers finish writing the summaries, we also ask them to annotate the summary focus area. The SFA is a rectangle area that covers the most informative elements for summarizing screens. It helps us understand where the labelers focused on when annotating summaries. We recruited 85 professional labelers and provided initial trainings before the labeling started. Each screen receives 5 annotations from different labelers. So in total, we labeled more than 112K summaries across 6,000 apps. Based on the data set we collected, we designed deep learning models to generate natural language summaries. From the highest level, our model uses an encoder-decoder architecture, which is common for image captioning and text summarization. It first encodes the mobile UI, then decodes the screen summary based on the screen encoding. Now let's take a closer look to the exact model. Firstly, we not only use the screenshot of a mobile UI, we also utilize multiple data modalities such as the app description and the view hierarchy. Next, we use the glove word embedding to embed the textual information in the data. We also embed the UI structural information such as the UI classes and bounding box coordinates. We then encode all this information using a transformer encoder. For the screenshot, we cropped each UI element and reshaped them to a fixed size. Then we encode the pixels using a ResNet encoder. We then concatenate the encodings from both encoders and feed it to a transformer decoder to generate the screen summaries. In our training experiments, we compare our models with heuristic baselines to validate the effectiveness of the proposed deep learning approach. We also compare multiple model variants that use different numbers of data modalities to see if multimodal learning achieves better performance. The results showed that our model significantly outperformed the heuristic baselines across all metrics. And our full model that uses the most data modalities achieves the best performance among all the model variants, validating our multimodal approach. Here are some examples of the summaries generated by our model. You can see that the full model is able to generate more accurate summaries than other model variants. To assess the summarization quality of our model with human judgment, we conducted a human evaluation using Mechanical Turk. And the results again showed that our full model achieves the best performance on subjective ratings. So we have had a dataset and a model that can generate high-quality screen summaries. We now propose potential applications where Screen2Words can be useful. Firstly, Screen2Words can enable language-based UI retrieval, with which a designer can retrieve UI designs by semantics using natural language queries. Screen2Words can also provide an overview description of screens to help screen reader users understand the purpose of an unseen UI more quickly. It can also be used to index mobile screens with language metadata to support conversational agents. For example, a user can easily navigate to a desired screen by announcing natural language commands with screen summary. Screen2Words represent a step closer to bridge mobile UIs with natural language. I will now talk about the limitations and future work. Firstly, our model is not always accurate. As shown here, it can produce generic or even wrong summaries. So future work can investigate new model architectures and evaluation metrics to achieve better summarization results. And to facilitate this effort, we open source our dataset and model code on GitHub. The link can be found in the paper. A natural extension of Screen2Words is screen question answering, which takes a mobile screen and an open-ended question as input, then output the answers according to the information presented on the screen. Actually, Screen2Words can be viewed as a special case of Screen QA, which answers the question, what's on the screen? But a full-range Screen QA can enable more versatile language interactions with mobile apps. We hope our work will encourage future work on bridging user interface and natural language. And that brings us to the end of my talk today. Thank you.